All right, so here are some properties of the definite integral. Now, because the definite integral is defined as the limit of Riemann sums, many properties of sums are also properties of the definite integral. Now, note that properties 3 and 4 here, this one and this one, are similar to the indefinite integral properties given in 12.1, whereas you can pull out a k here and then have k times the definite integral from a to b of f of x dx, and basically just pulling out a constant. And if you have the integral of the sum or the difference of two functions, you can split it into the sum or difference of two integrals altogether like that. So that's kind of a nice thing for 3 and 4. We've already learned those. We don't have to do anything different. They just apply them here. All right, property 5 is illustrated by figure 9, and that one basically says, okay, we're going to go from A to C, and what are we going to do? Well, we can basically take, if we're going from A to C, we're going to take from A to B, which is from here to here, plus integral from B to C. So we can split it up however we need to do that. And really the kind of the key thing is the overall area is going to be 2.71 because this is bigger. And what we're doing is we're taking the positive area, the B, which is 10.67, and we're subtracting off the ones that here are the negative areas. So the 2.33 plus the 5.63. So we're taking the two areas that are below, adding those together, and we're subtracting that off of the positive area, which is above, and we get 2.71. And that's kind of what 5 is doing. It would have been better probably if they would have said, okay, well, let's go from, A to 0 and then 0 to B and then B to C. But, in general, you can basically split things apart and add and subtract as necessary. Now, property 1 follows from the special case of property 5, in which B and C are both replaced by A. So if we're going from A to A, the integral area under that is going to be 0. And if you think about that, if we have a curve and maybe it's like that, well, A to A, that's just a straight line. A straight line is not going to have any area, so it's going to have an area of 0. Okay. And then property 2 follows from the special case of 5, where C is replaced by A. And so basically, we're going from A to B. Well, we're switching those around. And when we switch those around, that's going to be a negative, okay? And so that means if we're going from A to B here, basically what we could do is go from B to A, and we're just going to take the negative of it and get our value here. Okay, so that's some of the definite integral properties that we can use to help us solve some of these problems. All right, and that's how we're going to do these 5 problems. And so we're basically using these integrals. So some 0 to 2 for f dx, that's equal to 2. From 0 to 2 for x squared dx, that's 8/3. And from 2 to 3 of x squared dx, that's 19/3. So what we're just going to do is we're going to plug in what we know. Well, with properties of integrals, we can pull out that 6. And then that's from 2 to 3 of x squared dx. Well, x squared dx from 2 to 3, excuse me, 2 to 3 is 19/3. So we're going to have what? 6 times 19/3. Well, 3 goes in here too, 2 times 19. So that's going to give us what? 38. Okay. What about B? All right. So we're going from 0 to 2 of 9x squared. Okay. So let's split that into 9, 0 to 2 x squared minus, now let's pull out that 4, and we're going to go from 0 to 2 of x, forgot our dx, and our dx. So 0 to 2 x squared, that's this one. So we're going to have 9 times 8/3, then minus 4 times, looks like 2. So 3 goes into that, and okay, that's going to be 3 times 8 is 24, minus 8, so 24 minus 8, so that's going to give us 16 for this one. What about C? All right, so we're going to pull out 3, and so minus 2 to 0 of x dx. Well, notice we're going from 0 to 2, and they're going from minus 2 to 0. So what we can do, if we remember over here, we switch those, and we say, okay, well, that becomes a negative. All right, so now we're going to say, okay, well, that's equal to, and we're going to go from negative 3 now, from 0 to 2x dx. And that's going to be a negative 3 times 2, which is negative 6. All right, what about D? Okay, so we can, well, first off, doesn't matter here. If we're going from -2 to -2, that is going to be 0. That's just by definition. So we don't even have to worry about that one. A to A, it's 0. So no matter what our function is or what constants it is, that's just 0. So that was the easy one. All right, so E, 0 to 3, we can pull out that 12, x squared dx. All right, so what are we going to do here? Well, 0 to 3, well, we've got a 0 to 2, and we've got a 2 to 3. So maybe what we can do is we can say, okay, well, let's go from 0 to 2, and we have one piece. And then we can go from 2 to 3, and we have our second piece. Okay, so let's do that. So we're going to have 12 from 0 to 2 x squared dx plus 12 and 2 to 3 rather, x squared dx. Well, that's 12. 0 to 2 is going to be 8 thirds plus 12 times, and that's going to be what, 19 thirds. And if we plug all that together, I've already calculated that one. That's 108. Okay, so if you take all that, multiply it together, you get 108 for your solution for that one. All right. So again, that's how we can manipulate our definite integrals, pulling out a constant. What we can do is we can flip these around. We can split them apart and make it two of them. And we can also pull out the constants. Or, we have the one where we go from -2 to -2. That's just the area of 0. And then the last one, we had to break it apart and do one piece from 0 to 2, and then the last piece from 2 to 3. Okay. All right, so that's all I have for this section. Hopefully that will help.